So we will continue the introduction from the last lecture, and in this lecture I will give you an overview of what we are going to do in this course and a brief snapshot of each of those things. So the first thing that I would like to show you here is that in the last class we mainly talked about digital designs, right? So I have put the digital and analog design flows side by side to give you a comparison of how these designs take place, and consequently the verification problems in the two flows are also quite different. So on the left side I have the analog design flow, the digital design flow, where we start from the design concept, and that concept is typically written in English language documents. Then the design entry takes place. Now this design entry in the digital designs is typically in some language like Verilog or VHDL, and then to make sure that the entered design is correct and meets what was the original design intent, we do what is called behavioral simulation. So the simulation is simulating that code that was written in Verilog or VHDL with appropriate tests and checking whether the output that the simulation produces matches with your expected output. And once you are satisfied that yes, the code that I have entered is correct, then you go through the synthesis phase, in which the code is actually translated down into the design having your gates and flip-flops, etc. And then after synthesis, the different blocks, the different modules are placed on the floor of the chip, again in a symbolic way. We still do not have the silicon at this point of time. We just geometrically place the different blocks on the floor of the chip, and then routing means that we have to interconnect these chips, these blocks with to get the complete chip. Okay? And often this routing is done across the parts which are designed by separate designers. So again that is a non-trivial task, and the shape of the different blocks, their placements and the routing, this is all an integral problem, because if you place them badly then you will not be able to route them properly. If you place them properly, you are able to reduce the amount of interconnects to connect them. And then finally one can do post layout simulation. This is very much limited in scope because of the size of the design at that level of abstraction. And then we have the full chip assembly, where all the components of the chip are assembled together, and then full chip design rule checks, DRC stands for design rule checks, and then full chip simulation, which again is very limited, and then finally it goes to tape out. So this is the digital flow. If we compare that with the analog flow, the first main difference is that design entry, instead of being in some language, is directly entered through a schematic. So that means that you sit with a graphical user interface and start drawing all the components and connecting them together. Okay. Now once you have the schematic entered, then you do a simulation, and then you do a custom layout. After the layout, okay, you do the design rule checks and then extract a netlist from the design, and then you do a post layout simulation. Now in this space a lot of new things are beginning to happen. This space between the schematic entry, spice simulation and custom layout. What's happening here is that we are bringing in behavioral modeling here, where instead of entering the schematic directly, we first create behavioral models of the blocks. Okay, make sure that those models together are implementing the design intent correctly, and then build the different blocks. Okay, the advantages of this is that you get a feel of the whole chip before you have actually designed the whole chip, because you can make the models and plug them together and then see how the whole chip works. That is one advantage. The other advantage is as you start replacing each of those blocks with the corresponding designs, then the remaining blocks can be used as part of the test environment, right. So test means pre-silicon test, not the post-silicon test. So when you want to check a particular module, then the other modules are in behavioral level, so that the overall simulation speed is much faster. Okay. So if time permits, I am going to talk a little bit about this in this course. And then the later part of these, both of these flows is the same, that after post layout simulation it's largely similar to the digital design flow. So coming back to the digital design cycle, let us quickly go through the different verification problems at different levels. So initially we have a step which is called the intent creation. So what happens here is that as I mentioned in the last class, that there is a microarchitectural specification which is developed by the microarchitects at the beginning of the design cycle, and that is typically an English language document. And then what is done is people develop models which are executable. So they can be written in different languages like C or System C or STRL or Spec C, and then you run this executable and see whether it meets all your architectural requirements. Okay, so this is done several number of times until you are satisfied that yes, what I am hoping to have as the design intent is the correct design intent. After that is done, the output of this step is the specification documents of each of the architectural components, right. So at a processor level, that would mean that you have the functional units like the adders, multipliers, etc. You have the specifications of the number of registers that are there. You have some specification of the cache, okay, and the main blocks that are there in the processor. So these are the architectural blocks, and you have decided that what are the specifications of each of those. Again, this set of documents is typically an English language document. Then that set of component specification document is the reference for the designer to start coding the implementation using languages like Verilog or VHDL, right. Now at this point the design entry is taking place. So if you refer to the previous picture, that we had a step called design entry. So this is where the design entry is taking place. Now design entry is typically done by first coding the unit level module. So we typically have in the jargon that is followed in the industry, that you have a full chip level, you have the block levels, and you have the unit level. The unit level is the smallest granularity modules, okay, or in other words, they are the modules which typically will not have any other modules instantiated within them, okay. So it starts from coding those unit level modules, then you plug together the unit level modules to define a larger block, then you take a set of blocks and define another larger block, okay, and this is how the design coding takes place, all right. And then the design integration phase is putting everything together, right, so that you finally have the integrated design of the whole chip. So in this level, when we are coding the Verilog and integrating the design, what can be our reference? How do we decide that is correct or not, right? So at this level we have to compare the design with the specification, but the specification is in English, so how will we compare with that? So there are several approaches which are taken. One is that you could have a previous implementation which has the same functionality but a different architecture. So you could use that and compare the results of that with the results of your simulation, okay, that's one option. The other option is you had that C-spec model in the previous slide, and that also is going to give you at certain points of time the expected outputs. So you could use those outputs as the golden outputs and compare it with the outputs of your simulation, right? And the third and more interesting thing which is coming up is that we could have properties to specify what is correct and what is wrong. Like for example, in a system you want to say that these functional units will never be active at the same point of time, right? That's a property, and then you try to verify that whether that property holds always whenever you simulate, or statically if you are able to deduce that in this circuit these two modules are never going to be active at the same time, right? So that is formal property verification. That's another aspect which has come up. Then after this design, the design has been verified, then the steps of synthesis and technology mapping to take it from the gate level netlist to the transistor level, this has the property that there is logical equivalence between these steps. So the methods that are used for checking the equivalence between them are typically called equivalence checking methods. But equivalence checking is mainly intended here to check the functional correctness of the design, but we have several other things to check also, like what kind of power does it consume, does it meet the timing requirements, okay. So all those are additional verification problems, in addition to making sure that the design has been correctly synthesized in terms of the functionality. By functionality I mean that whatever output you expect it to produce, whether it is producing that output, okay. But timing means whether it is producing that output within the desired time, right. So that's a different thing altogether. And then after the transistor level design has been verified, then you go to layout, and then the mask generation takes place, which is the one which is fed into the fabrication machine. So in this whole flow, more than 70% of the design cycle time, or the time that it takes from the concept of the chip to the final implementation, is spent in verification. So this is a slide which shows you roughly the breakup of the times in the design cycle, and the source of this is from a presentation made by Zero in Design Automation, which is a company which works on verification solutions. So you see that here the major chunk of this is spent in simulation, okay, almost 46%. That involves architecture level simulation and system level simulation. So that means that you integrate the entire RTL and then simulate that, and that simulation takes a huge amount of time. And also behavioral modeling. Okay, so all of these takes up 46% of the time. This is the major chunk of the verification. And then if you look at the design, the functional design, it takes about 27% of the time, within which again you have this block level simulation, which is also part of the verification. So when you develop individual blocks, then you start simulating those blocks, so that also is taking up your time. Okay. Then you look at the structural design part, in which you have the synthesis, and then timing analysis, that's again another part of the verification problem. Equivalence checking, that's also verification, okay, and then DFT. And then emulation is basically creating a prototype of the design in hardware, okay, using FPGAs or the like, and then checking whether the design works correctly. This also is part of verification. Okay. This is the part of the verification that I showed you in the first slide in the first lecture, when I talked about the verification problems before silicon and after silicon. Okay. Now this is really growing, because people are feeling that simulation here with 46% of the time is quickly running out of steam, because the larger the designs are, the more time that it takes to simulate them, and getting adequate coverage in simulation is becoming a problem. So people are saying that why don't we get a first silicon out quickly and then do most of the verification on that first silicon. The advantage is that the silicon runs much faster than simulation. Simulation is running on a processor, right? And the silicon is going to run on its own clock speed, which is pretty high, right? So why can't we do the verification after taping out the first silicon? The good thing of that is speed. The bad thing about that is you hardly have any visibility, because you just have the interface pins. You cannot probe any signal within your design as you like, right? And in simulation you can always do that. You can actually check the values of any variable that you want during simulation, right? So this is a major problem. But think of the people who have been working on testing. They have been doing testing of the whole chip by just looking at those pins, and they have things like scan chains to, to actually read the state of the chip. In other words, the state of the registers, by having a connection between the registers so that you can drag out the contents of the registers whenever you like. Okay, you can't do it too often because it's going to slow down your testing, but you can do it once in a while. So that gives you some visibility about the internal state of the chip, right? But these two technologies are beginning to converge now, and what is happening is we are having post silicon verification. All right. So hopefully towards the end of the course we plan to give you some overview of this new trend, okay, because this is testing and verification course, so we should at some point of time show you where the two are converging. This is a picture which shows you the pieces of the verification puzzle. So this is the gamut of the verification problem. So one thing is that you have unit level validation of the individual blocks, cluster level validation of blocks together, and then full chip validation when you have put everything together. And these are the diverse types of problem. First thing is architecture validation. Is the architecture itself correct? Then microcode validation. The microcode is actually controlling the entire data flow through the architecture. Is that correct? Then power validation. I want to make sure what is the kind of power that the chip consumes. So analysis of that power and verifying that it remains within bound. Protocol validation. So all these chips have a lot of on-chip protocols. Protocols for communication between the processors and the cache. Protocols for communication between the processor and the memory. Okay. So all these protocols they need to be validated, and you have to make sure that the components of your chip are actually following the protocol correctly. Okay. Then debugging validation. How do you debug when you have found an error? How do you track the source of that? And then timing validation. So this again shows the scope of property checking and equivalence checking. Specifications, microarchitecture, RTL. At this level, we don't have any golden reference model, so we can use property checking. And then lower down, we will do equivalence checking. So broadly speaking, the functional verification challenge is as follows: that we want to make sure is the implementation correct. How do we define correct? So in the classical is that simulation result matches with golden output. In formal, we check equivalence with respect to a golden model. That model is a formal model of the system. And in property verification, we check the correctness properties which are expressed in a formal language, and then checking those properties on the implementation can be done either formally, and then that technology for checking the properties formally is called model checking, or it can be done in a semi-formal way where I cannot give you complete guarantee about the correctness of the property, but given more and more time I can improve my confidence that the property holds on the design. Okay, so that's semi-formal, and there is a trade-off in all of these three between the complexity of doing this verification and the exhaustiveness. So if you want 100% confidence, then the time complexity of the thing is going to be pretty high. Okay, if you have one reasonable confidence, you can bring down the time complexity. Right? So there is a well-defined trade-off between these, which we are going to study. So this is a picture which shows you the simulation flow. So first thing is that one component is the design. Okay. Now after the design we have the test bench. The test bench is a wrapper around the design which invokes several tests. So what are tests? It defines the inputs that are going to be driven into the design. Alright. So just to give you an analogy in software, suppose you write a software program, right? How would you test it? So you might say that I will execute the program and I will feed in inputs and see whether it works correctly. Now if you have millions of inputs, then you can't manually feed it. So you will have to write another program or another input file which is going to feed the inputs into your program, right? And in that case, if you have that, which is, and then you pipe this whole thing, you have this input file and then you pipe it into the program. Okay. So which is the wrapper here? The wrapper is the shell. The shell which is taking your program, which is taking the input file and feeding it into it. So the test bench here is that wrapper. Its job is to take the tests which can also be written in Verilog, which are in fact typically written in Verilog, and it integrates that with the design so that when the two are simulated together, the tests are fed into the design. And similarly, the outputs from the design may be recorded or dumped. Right? Now, alongside this test bench, we have a very important thing which is called the test plan. What is the test plan? The test plan is your definition of what needs to be tested. Okay. Now this is typically, you start doing that by writing an English language document. You study the specification of the design and then the test team starts writing a test plan. So they say that, okay, to verify this design we need to test this thing, we need to test this thing, we need to test this thing, and so on. Okay. Then enumerate all that. Now when we are actually running the test bench, we need to make sure that which of those tests have been covered, right? So how is this test plan used? It is used to generate the stimulus. Okay. Now what is the stimulus? These are those tests which the test bench will drive into the simulation. Okay. So from the test plan to stimulus generation is today mostly a manual step. You take the test plan document and code in the different tests that you will run on the design under test. Okay. Another jargon which would be useful to remember is we refer to design under test as DUT. Okay. So when I colloquially suddenly say that we are going to drive this into the DUT, it refers to this design under test. Okay, please try to remember this jargon. Then today there are now new kinds of languages which are coming up for expressing the test plan in a more abstract level, and from that the actual stimulus generation is being done automatically. Okay. The other important thing here, which is also a relatively new thing which has come up, is coverage matrix. Now coverage matrix in the classical sense had been around for many years. What does it do? It checks whether every line of the Verilog code has been covered. It can check whether every transition has been covered. It can even do things like state coverage, whether every state bit has toggled once. That's toggle coverage. Okay, whether certain wires have toggled at least once during the simulation. That's toggle coverage over the signals. So there are different types of coverage metrics like this, and those coverage metrics are monitored all the time during simulation. Alright. There is an increasing emphasis on linking these two up. Okay, that when we decide what are the functionalities that we have to test, how can we test those, that whether those functionalities have been covered during simulation. But then the coverage metrics cannot be things like stuck at faults, or it cannot be things like just toggle, etc. Then we have to model functionality there, right? So one important interesting thing that has come up is then that you again write properties. You write properties saying that uh, that whenever this signal goes high, then within 5 cycles that signal must go low. Now if you want to check this property, then the first signal must go high at some point of time, otherwise you have not checked anything. So you can express that again in as a property here, and they are called cover properties, right? And just like any other coverage matrix, at the end of the simulation you produce a coverage report saying that these properties were checked, these properties were not checked because their conditions never happen, okay? And in terms of simulation coverage metrics like code coverage, transition coverage, etc., the separate report is produced on that. We will study these things in more details when we go into how the simulator works. And then after the simulation results are available, then you debug and make sure that whether there are any bugs that have come up. In other words, does the simulation output differ from your golden outputs? If so, then you do a bug tracking and then go back to the design to change the design, and then again go through the whole flow again. Okay. Now the advances that has taken place in recent times, as I said, is that test bench languages are richer. Languages like System Verilog, where you can do almost everything. It's almost a C-like language for developing your test bench. Like you can have fork join, you can have semaphores, okay, you can have multiple threads. So that's very nice because it helps you in modeling very complicated scenarios. And then there are coverage monitors and assertions, which we are going to study. And then test benches have become layered, and there is a term called transaction level modeling, which has become very popular. Okay, we will talk about these things in due course of time. Now this slide talks about the advent of formal methods in EDA. EDA stands for electronic design automation. The goal of formal methods is to do exhaustive verification of the design intent within feasible time limits. Simulation is not exhaustive. It depends on the test scenarios that you have generated. And you cannot generate all possible test scenarios, because for a large design that will be so large, the number of possible exhaustive set of test scenarios, that we will never be able to run simulation on all of them. But formal methods tries to score over that by saying that whatever we check will be exhaustive. So we may not be able to check everything with formal, but whatever we check will be exhaustive, complete guarantee. Okay. The philosophy of this is that we extract formal models of the design intent, and we extract model from the implementation and compare them using mathematical or logical methods. So we have formal properties in the design intent, then we have the register transfer level code, then you have gate level, transistor level. As I mentioned before, that at these levels we have formal equivalence checking methods. Equivalence checking methods that formally tells you that these two are equivalent, these two are equivalent. And on the top you have the model checking, which is checking the properties against the RTL. So brief history of that is that temporal logics, which form the basis of the languages for specifying properties, was developed a couple of decades ago. And the person who was mainly the main contributor behind that, Amin Newelly, he received the Turing Award for that contribution. Then very quickly the temporal logics were adopted into industry specific languages by Accelera, and then finally handed over to IEEE. So the language standards like System Verilog, Assertions and PSL, they are IEEE standards today and widely used in the industry, and they were integrated into System Verilog. And within quick time there were a lot of tools that came up from the academia there were tools like new SMV, which is the CMU formal verification tool, and VIS, which is the Berkeley formal verification tool. And the industry was also very quick to come up with their products, and today we have Magellan from Synopsys and IFV from Cadence. These are very powerful formal verification tools. And this year, Clark and Emerson and Sifakis, I missed the third name, they got the Turing Award for their contributions on model checking, or the formal methods for checking the correctness of properties on the implementation. Let's give a quick example of what formal properties and formal verification means. So suppose we have a priority arbiter. So we have an arbiter which has 2 requests and the corresponding grants. Okay, and the arbiter has to decide that which request will be granted at which point of time. So let's see the first property. This property says that either G1 or G2 is always false, in the sense that an arbiter is not expected to give grants to 2 of the outputs at the same time. Okay, that's a generic property of arbiters. So we can express that in this logic, which is called linear temporal logic. We are going to go into details of this logic later on. So to just get a flavor of this, this says this G says always or globally, G for globally. Okay, it says always we must have not G1 or not G2. Okay, so either G1 should be false or G2 should be false, always. Okay, so globally not G1 or not G2. Let us look at another property. Whenever R1 is asserted, G1 is given in the next cycle. This says always whenever we have R1, that implies this X stands for next. In the next cycle we have G1. So always R1 implies next G1. Okay. Third property, when R2 is the sole request, G2 comes in the next cycle. Now R2 is the sole request means what? Which means R2 is high but R1 is low. Alright. So always R2 and not R1 implies next G2. Okay. So which has the higher priority? R1 has a higher priority. So whenever R1 is high, it must get the grant in the next cycle. When R2 is high, it will get the grant in the next cycle, provided that R1 has not also requested. Okay. And when none of the devices are requesting, then the arbiter will park the grant on G2. So the low priority request by default has the grant. Okay. And when the high priority request comes, it gets the higher priority. But whenever R1 is not requesting, then at that point of time the grant is normally going to reside with G2. Right. So always not R1 and not R2 implies next G2. Alright. So this says that whenever none of them are requesting, then next cycle G2 should get the grant. Now suppose someone has given us this implementation. The RTL designer has coded this implementation. What does this implementation have? It has 2 flops, an AND gate and a NOT gate. Okay. Now let us see whether these properties hold on the design. So first property is checking whether always not G1 or not G2 will take place. Okay. So to see that, we see that when R1 is high, then in the next cycle G1 will be high, but if G1 is high, then when R1 is high, then this one will drive this to 0, so G2 will be low. Okay. and when R1 is not high, then G1 will be low in the next cycle, right? So at each point of time we have either G1 or G2 is low. If R1 is high, then in the next cycle G2 will be low. If R1 is low, then in the next cycle G1 will be low. And in every cycle R1 has some value, so in the next cycle either G2 or G1 will be low. So that is satisfied. Let us look at the next property. When R1 is asserted, G1 is given in the next cycle. That's obvious because of this path. Okay, R1 is asserted, then G1 will come in the next cycle. When R2 is the sole request, G2 comes in the next cycle. If R2 is the sole request, that means R1 is low, so this is high, and R2 is high, so this AND gate's output will be high. So in the next cycle we will have G2. So that's also satisfied. When none of them are requesting, the arbiter parks the grant on G2. So if both of them are low, then what's going to happen? Both G1 and G2 will be low. So that is a violation. So we deduce that out of these 4 properties, the 4th one is not satisfied. Now the model checker, the property checker, is going to throw up this property and say that look, this is not satisfied, and it will produce a counter example. What is a counter example? It will show you that look, when R1 and R2 are both low, then in the next cycle we have G1 and G2 are both low. Right? So that's the scenario, that both R1 and R2 are low, is the one which will demonstrate that this property does not hold. Okay. Now these properties are checked in 2 ways. One is what is called dynamic property verification, where this is what happens, that the property specification is entered by the user using some language like system verilog assertions or PSL. And this is the simulation platform. So here is the device under test, the design under test, which is the duty, and we have the environment of that, which is modeled by the test bench. Okay. Now in these modern languages we have the concept of an interface, which is one of the new things that came up when we had system verilog developed out of verilog. What this interface does is that you can define that these are the variables in the interface, and you can bind the interface to this side as well as this side. Okay. How does that help? The assertions can be coded using these variable names. Right. So regardless what are the variable names used in the duty and in the test bench, you can write the assertions using this, and then binding is actually, attaching the names together. So my signal R1 here may be called as REQ1. Okay. So the binding is telling us that R1 is REQ1 here, and on this side maybe this is called as Z1. So we are saying R1 is Z1. Okay. So that's how you bind the thing together, and this interface is what is made visible to the assertion monitor. Right. So the complete simulation runs like this, that the test environment drives the inputs into the device under test and samples the outputs of the device under test, but this whole interaction takes place through the interface, and the monitor actually reads the samples the signals on the interface and checks whether there is any violation of the properties. Right. So as the simulation progresses, it keeps tracking all these properties, and whenever there is a violation of any property, it flags an error. Okay. So we are going to see how we write these assertions, how we can plug them into the design, how does the simulator work with these monitors. Okay. And then how can you club that with the coverage definitions and make sure that you have adequate coverage of the design with respect to those properties. Okay. The other method is the static method, which is called formal property verification. So there the approach is as follows, that from the device under from the design under test, we extract a state machine. Now this is a very non-trivial step, but it's a feasible step, because you see, when you have a Verilog code, the synthesis tool is actually extracting the state machine, because it's giving you a design which has gates and flip-flops, right? So it is doing a state machine extraction. So it's a feasible step, but complicated. And then you have these properties, and the model checker is going to take the extracted state machine and the properties and check it exhaustively on that state machine. Now the whole problem is that the classical method of model checking requires that the state machine be provided explicitly. In other words, that it has to explicitly traverse the state machine to guarantee that the property holds, right? And for a typical design, this state machine is going to have billions of states. So the whole challenge is, how do we check those properties on these billions of states without getting into too much of complexity, right? So there what we try to do is, we try to use different kinds of reductions. We take the property and try to figure out which portions of this state machine is relevant for this property. There might be parts of the state machine which are not going to affect the truth of this property. Okay, they are components of the circuit which have got nothing to do with this property. So we can prune that out. So pruning out the state space, creating abstractions, checking the properties on those abstractions, and if necessary again refining the abstractions so that you reach a level where you can say with 100% confidence that this property holds, is a whole bunch of problems which is very interesting. Okay, and we are going to study that in reasonable amount of details. The other interesting thing is that instead of getting 100% confidence on that, can we get approximation? Okay, so that's another aspect of that, and there are new methodologies coming. Third important thing is, how do we represent the state space? Right. So if you have a few states, you can think of a graph. Okay. If you have billions of states, how are we going to represent it? So how do we represent it in the circuit? In the terms of functional relations. So Boolean functions. Boolean functions help us to represent functions which can involve lots of states in just a few literals. Okay. But then if you have it in that form, it is difficult to traverse it. How do you go from one state to the next? You have to repeatedly apply that function to do that, right? So there are other methods for representing state spaces which are very large, and that includes things like binary decision diagrams or SAT. SAT is our classical Boolean satisfiability, and there has been an enormous development in the literature on how to traverse state spaces using BDDs, using SAT, using combinations of these. Okay, so that is something that we are going to look at. I will skip this slide because this is going to come later on. This talks about the way in which the formal tool is used today. So you start with the model for the plus the properties, you run it to a model checker, and then you typically end up with indeterminate results, which means that you can't infer whether the property holds on that. Okay. If it is indeterminate, then you go back here and further create an abstraction, create a new abstraction, again try this, and you can go around in this loop several times. Okay, and if you still cannot prove the properties, then you realize that these properties I can't prove with formal. So then you go into what is called bug hunting mode, or which is directed simulation, the other thing that I talked about, that you check the properties over simulation. Alright. So if initially if you start with the entire design and the properties, almost always you will not be able to solve it, because the formal engine will run out of capacity. It will start taking up so much of memory to represent the state space that it will not terminate. So you will have to go around this loop, creating smaller and smaller abstractions until it runs. Then when you have an abstraction where you have some result, you still do not know whether that result is a valid result or not, because you have proved it on an abstraction. So then what you do is you check that counter example on the design to check whether that is spurious or not. If it is spurious, then you refine the abstraction and then go back here. If it is not spurious, then you have the bug. Okay. Otherwise, you have to go back here. All right. And on the other hand, if you did not have a counter example here on that abstraction, then you are happy, because you have proved that the property holds on this. These abstractions are created in such a way that if your property passes on the abstraction, then it is guaranteed that it is going to pass on the actual design. If the property does not hold on the abstraction, then it generates a counter example. That counter example can be spurious. It may not actually be there in the design, which is why we have this refinement step. Okay. So how to create those abstractions such that you are guaranteed that whenever the property holds on the abstraction, it holds on the actual design. That is again another technology. Okay, and we need to study that. This is the agenda of the course. So we are going to have from the next lecture a brief overview of Verilog. Then I am going to talk about how simulators work. How do you do a simulation? Right? Then we are going to talk about how do you generate test scenarios, how do you monitor coverage, what do those coverage mean, okay? How do you assess the amount of confidence that you have in your simulation by virtue of the coverage matrix. Then we are going to look at static checks. There are a lot of checks that are done even before you start simulation. There are checks which catches several common errors from the design before you run even one cycle of simulation. Then we are going to come into symbolic representation of logic and state spaces, BDD, SAT, etc., reachability problems, abstraction problems, refinement problems on that. Then we will use all that stuff in equivalence checking, and then we are going to talk about assertions or formal properties, then model checking, and then finally we are going to talk about something which is pretty hot topic these days, which is formal verification coverage. How do I know that I have written enough properties? Because I can write properties which are absolute garbage. They don't mean a thing. I can write properties which are always true. Right? So if when I have checked a few properties, what can I say about my confidence in the design? So how do I pitch the functionality of the design against the properties that I have checked? So that's the last topic. And then we can have some additional topics like verification in the analog domain and things of that type. So we have a verification group here, as you may be aware, where we work with several companies on different problems. So these are some of the problems on which we have been working with these companies. So we have been working with Intel for about 5-6 years now, National Semiconductors. We work on the analog mixed signal design verification space with these people, and incidentally, I've been shut out. So anyway, so we work with National Semiconductors on the analog mixed signal design space. We have been working with Synopsys for almost 10 years now on different RTL verification problems. And then we have a new project from IBM on the gate level verification problems. Then we have we work on other spaces of verification also. We work on automotive control system verification with General Motors. and on web interface verification with Google. So besides this, we also had previous projects with Sun Microsystems, and we have partnerships with another company called Intera, which is probably the only well-known completely Indian EDA company. Okay, uh, so we will talk about that more later. So with that, we conclude this lecture. Let's take a small break, and then we'll come back for the next lecture.